We're going to go over a couple of examples that illustrate what we term Hess's law. Hess's law is a technique for finding the enthalpy change for a chemical reaction. You've already done a lab investigating Hess's law and were able to experimentally verify its validity. So now we're going to look at some problems, 3 problems in total, that illustrate using this technique to find the enthalpy change for a reaction. So if you look at your sheet that I gave you, I'm trying to find the enthalpy change for a given reaction. There you see it at the top of your paper. That's our target. What you have available to find the enthalpy change are 3 reactions that someone already have conducted and have found the enthalpy changes for. We're going to try to combine these 3 equations so that they give us the target equation. So I decided to begin by looking at reaction 1, and I flipped it. And when I do, it looks like this. Now the reason I'm flipping it is I'm keeping my eye on the target, and I see that I want sulfuric acid, H2SO4. I need it as a reactant in my target equation. Of the 3 equations I was provided with, reaction 1 is the only one that contains sulfuric acid, and I just had to get it into the right position by flipping it. Now when I flip it, that means that the sign of the enthalpy change for this reaction changes. It was negative in the original reaction 1, but in the flipped version it becomes positive. Next, I'm going to take reaction 2 and I'm going to leave it alone. And it would look like this. And the reason I'm using reaction 2 is I need to get sulfur trioxide and water as products in my target equation. This equation gives me that sulfur trioxide in the correct position. Because all I did was use the original equation 2, I do not alter the enthalpy change. Finally, reaction 3, I'm going to flip it. I'm going to leave it alone. And in this case, I'm using reaction 3 to get water as a product, but I need water vapor as a product. If you look in reaction 2, I have water as a liquid as a product. So this is the one that gives me the proper form of water, so I'm leaving it alone. And of course, I don't change the sign of the enthalpy change. Now, what I'm going to do is I'm going to add these equations together, just like you did for the equations from your lab. Things that appear on opposite sides of equations will cancel. So let's go through these and see if anything cancels. Well, first of all, the hydrogen sulfide, it cancels out, it's on opposite sides. The 2 molecules of oxygen, opposite sides, they cancel. And water as a liquid cancels. So now, everything that survives, which I'm going to highlight, I have 1 reactant surviving, I have 2 products surviving. I'm just going to bring those down, and they represent the summation of these 3 equations. And you notice I now have an equation that matches my target equation. And as I added the chemical equations, I will add the enthalpy changes. I'm going to add these 3 numbers together, and my final answer is a positive 72.5 kilojoules. I was able to find the enthalpy change for a reaction by knowing the enthalpy changes of other reactions where the enthalpy values were already known. You can do these in different order. You can try different approaches. Ultimately, though, you have to end up with the target equation, and the summation will give you the enthalpy change for it.